I'm going to talk today about data compression. And just so that we're all on the same page, here is in a nutshell what we're going to do. This is a file. It's a bunch of zeros and ones. It's a sequence of zeros and ones. And we want to make that file smaller, as in we want to write the same information with fewer digits. That's what we're going to do without losing anything, without throwing anything away. And the question is, how is that possible? And the answer is a bit more elaborate, but it involves machine learning. So the kind of things that people want to compress are not limited to sequences. There's all sorts of stuff, but a lot of it goes into human text, pictures, of course, video, but also source code, computer binaries, and all sorts of structured things like data sets or even unstructured data like multisets and sets. And why do we want to compress? Well, the answer is that, first of all, it lowers the storage and transmission costs, right? So you can put more on your existing hard drive, you can put more on your existing data center, simply by re-encoding how you're writing down the information. Just by changing how you're writing it down, you can make better use of your existing infrastructure. We can transmit more data using the same bandwidth. So that, for example, could mean even if you can't upgrade your cable, suddenly the video quality is so much better because you found a way of writing down that video in a much smarter way that allows you to reconstruct more of the image without changing anything else. And it also turns out, and that's kind of beautiful, that it gives you efficient, exact sampling methods. And you've already heard a lot about sampling methods today, but I'm going to go into that a bit later. So here's our friend on Mars, and that's a pretty expensive project to get him there, but it's also pretty expensive to get the data back from it. So there's an information bottleneck, and if we had a smarter way of encoding the information, we could, say, double the amount of pictures we could get back from Mars. We're waiting for the data link, and we could have so much more data if only we knew how. Now, the nice thing is that the software on the rover can actually be changed, and we can change our software down here on Earth. And if we wanted to, we could find a way of making a smarter communication link so that we suddenly get twice the amount of pictures or measurements out. So that's the motivation. Just to be clear, there are two kinds of compression that are typically distinguished. One is lossless compression, and that's what we're going to talk about today. Here, the idea is that we're throwing nothing away at all. So we're perfectly preserving the information that there was to begin with. We're going to have an encoder that does something to the data originally, and the decoder can perfectly recover what came into the encoder in the first place. There's also a second type of compression, which is sometimes called lossy compression. And here, the idea is that it's okay to throw away things that we don't care about. You may have heard of JPEG and various video codecs that really think, like, well, we don't really care about the exact color of every single pixel. So let's just give you something that's approximately the same that a human can't possibly distinguish. The same for MP3, an audio format that uses perceptual coding to essentially not even bother with frequencies that we can't hear. So that's a whole different form of compression. We're not going to do that today, but it's also very useful and very helpful. A third type of compression is that people sometimes hear about these days is neural network compression. What they mean is we're taking an existing neural network and we're transforming it into a network that needs fewer parameters. That's not really the same as talking about the inputs and outputs, except if you want to ship a neural network that's huge to a Mars rover, say, pre-trained and everything. But that's not really what we're talking about. If anything, it belongs into lossy compression because we're really thinking about a way of building a different network that has similar properties to our original neural network. But again, we're not doing that today. We're focusing entirely on lossless compression, where there's an exact inverse transform. We can get everything back. And you may have heard of zip or PAQ, or even the FLAC file format. That is an audio format that essentially compresses audio files without throwing anything away. It can't make files quite as small as MP3, but a lot smaller than just storing the waveform. And it can give you the exact original waveform back. So let's have a go at data compression. So the key idea here is, right, that we want it to be a reversible transformation. Nothing's thrown away. And some files are going to be more common than others. So what we're exploiting is that if we can make the really common files smaller and the very uncommon files slightly larger, then it's a net win. Then on average, we expect that because the common files are common, that we can reduce the amount of information. But no compressor can ever promise you to make every file smaller. The way to see that is the Pigeonhole Principle. So there simply isn't a way of making every file smaller without throwing something away, right? So if you imagine that you could make every file smaller, then by recursive application of your compressor, we could reduce every file to a single bit or maybe to 0 bits. And clearly that's not sensible. So it costs us something. And that cost ultimately will be written down in the form of a probability distribution. But we'll get there. But before we start, here are a few famous compressors that you may have heard of. So gzip is, I'm sure everyone has heard of that. It's a very old compressor, and it was not made with any machine learning knowledge, really. It is this amazing algorithm that someone came up with, and it took us ages to even understand how it works and exactly what the distribution is that it's modeling. But it's very fast, very popular, and still used all over the world today in various forms. There's also bzip2 that some of you may have heard of. It tends to compress a lot of things better than gzip, and there are several reasons for that. But again, this was an algorithm that didn't explicitly model probabilities at all. It just does some very weird thing to a large chunk of data by essentially permuting the data in a particular way. And lo and behold, it seems that it's easier to compress it afterwards. And it's entirely lossless. Black magic. No one understood it for quite a while. Turns out it actually is related to a probabilistic model. And it can be reverse engineered from the code, but it's very hard. There are many other kinds of algorithms. Perhaps one worth highlighting is PPM that you may have heard of. It's often used, or variants of this kind of algorithm are also used in text prediction. So when you're typing on your phone and your phone is trying to help you by suggesting what you might want to type, these are the sorts of algorithms that are underlying those predictions, language models. And ultimately, language models and compression algorithms are one and the same thing, and I will show you exactly how they link up. So instead of ad hoc algorithms, which are lots of fun to construct, and I encourage you to play with it and think of something that you can compress just by a set of rules. But instead of doing that, we will use probabilistic models for compression. And to compress some probabilistic model, we'll define a probability distribution and then construct an optimal compressor for that distribution, as in for objects that are distributed according to that distribution. And the better that P models our data, the better our compressor is. So it's really a nice game to play. So if you're a machine learner, the more you can throw into the model, the better you can model your data, the better the compressor will be. It's magic and amazing. So all that you're learning right now is going to be relevant and helpful. But before we do that, let's review some basic theory about codes and information. So, codes. What's a code? Essentially, there are many different ways of writing down information digitally, and any such choice, any such rule book is called a code. And essentially, a code defines a mapping between a set of input objects, so you define your universe, and sequences of symbols from some finite alphabet, typically the binary one. And to get this started, we're going to play a little game. I'm going to ask for a volunteer to think of a number from 0 to 63 inclusive. You need to be able to answer some basic yes and no questions. Who can think of a number? I know it's been a long day. That's like a few bits of entropy right here. Okay. Do you have a loud enough voice to shout out answers? Okay, excellent. You win. Now, I want another volunteer to think of a number from 0 to 63 inclusive without shouting it out. And we're going to play a little game. In particular, I'm going to guess what the number is. So who wants to have a go? Who has a number? Okay, do you have a loud enough voice? Yes. Great. So you've chosen your number. Okay. Tell your neighbor so that you can't cheat and change your mind. Tell him quietly. Okay. Now, I'm going to show you a bunch of questions. The first question is the number on this slide?
Yes, it is.
Is it on this one?
No, it's not.
On this?
Yes, it is.
And here?
Yes, it is.
And here?
No, it's not.
And here?
No, it's not.
Okay. Now, did someone get the answer? No? So the answer is 42. That was the number the gentleman picked. And my question to you is, why did you not get the answer? How come you missed this? But okay, let's recap what happened here. So each of the slides, right? Each of the questions had the form, is the kth bit of the number equal to 1? Think about this for a moment. So each slide contained only those numbers that had a particular bit set and didn't care about the other bits, right? So the nice thing about these questions, I can show these slides in any order. They are conditionally independent, but I get exactly 6 binary questions. That gives me 6 bits of information, and that's enough to reconstruct a number from 0 to 63, right? So the binary representation of 42 is 101010, and that essentially corresponds to the answers that were given in some permutation. Note that it didn't have to be that way, right? I can actually pick my questions, and as long as they bisect the search space, I can still reconstruct the number. So here, I've chosen different questions, right? So again, if we go with 42, then this alternative strategy would have been, I could have as the first question, is it smaller than 32? The answer would have been no. So I would have asked, is it smaller than 48? And so on. So I bisect the search space, sometimes called binary chop. And if you search through a sorted list, that's a common thing that people implement. And that works equally well. But the order of the questions matters suddenly. I can't permute the questions. And secondly, each question depends on the answers to the previous questions, right? So it's not quite as fun and not quite as easy. But the real thing is, I actually want you to be able to do this in your head. So I'm going to show you a trick, and we're going to do this one more time. So first, I need a volunteer who can think of a secret number so we can test it. Who is ready to think of a number between 0 and 63? Someone here, maybe? Yeah? Excellent. So I'm going to teach all of you the algorithm so that next time you don't have to laugh, but you can actually do this in your head. And it's very, very simple. So the numbers on the slides are sorted, and the lowest number on the slide, right, is going to be that has all bits 0 except the one that has the 1. So all you have to do is add the first number of the slide when the answer is yes, and do nothing when the answer is no. So it just comes down to doing a bit of arithmetic. So I'm going to play this game with you, and you can see if you can get the answer before I get it. All right, are you ready? You still have your number? Okay, is it on this slide? No. Is it on this one? Yes. Is it on this one? Yes. Is it on this one? No. How about this one? No. This one? Yes. Did someone get the answer? Shout it out. 37. Correct. Well done, guys. Okay, so you're going to learn some magic tricks. This is pretty fun. So you can just print out these slides, or you know how to construct them, right? You can have like these cards in your pocket, and you can play this as a party trick for certain kinds of parties where that would be fun. All right. So our questions, right? The questions that we asked, this game that we played, define a mapping between objects in binary sequences. So, and any such mapping is called a code. So we define codes. And Another way to think about it is you can think of it as a decision tree. So here, you can sort of imagine that we're bisecting the search space. Here we have numbers from 0 to 15, so we have 16 things to choose from. And we can sort of visualize it as follows, right? So the first answer for some question that we're going to get gives us one bit of information and splits the search space in half. Then we can split it in half again, and in half again, and in half again. And after receiving 4 bits, we have a number from 0 to 15, right? That's one way of visualizing it. Now, that was when the distribution over numbers was uniform, but it doesn't have to be uniform, right? You can have any distribution over numbers, and you could imagine bisecting the search space in such a way that you try and group as much probability mass together that you roughly end up with equal halves, right? So maybe this half here is roughly as much as this whole remaining half, and or maybe not. And so if you group these together, your first bit could choose which of the 2 halves it's in, and so on. So you could bisect that space more and more, and you would essentially end up compressing something that has a different distribution from uniform. And if you do this optimally, then your set of questions will be minimal, as in you want to minimize the number of questions you need to ask so that you can identify any point from your space. Okay, so, and of course, distributions can look a bit more messy. So this, for example, is a much more typical distribution that you might encounter. And the partitions that you make when you bisect the search space doesn't have to be contiguous either. So you could imagine grouping different things together in order to choose your questions. And that's just like with the question game earlier, right? It doesn't matter which questions we choose as long as you get enough information out. And you can choose for convenience or for ingenuity. And you really need to work with whatever distribution you have. Right. So a code defines a mapping between objects and binary strings. And of course, you can have other alphabets too, but I'm just going to make things simple, and we're going to assume for now that it's all binary. So we have binary strings and we have objects, and we want some sort of mapping between the two, some lossless mapping, in some way that the encoder computes the code word from the object, and the decoder can recover the object from the code word. So codes can be designed for lots of different purposes, not just compression. For example, a very common one is to standardize ways of communicating. You've all heard of the ASCII code or of UTF-8. These are codes that were designed just so that we're all on the same page, so we all understand what, for example, the letter A stands for. So we've all agreed we want to send English text to each other. We have an alphabet that we agreed on, but we need to somehow figure out what bit code corresponds to which letter. And that's exactly what these codes are for. They do nothing other than standardizing a way to communicate. We also have codes for error correction. Here the rough idea is that the message can get corrupted on the way, and we want to make sure that if the corrupted message arrives, the receiver can somehow magically recover with great confidence the original message that there was. So that's pretty magical, and it kind of comes at a cost, as you can imagine. The message may have to become slightly longer so that you have extra information that can help to recover for certain kinds of errors. We'll talk about that a tiny bit later today. Then there's encryption, where effectively we're trying to make it as hard as possible to read the message, except if you're in on the secret. And there's also authentication and all sorts of other cool things. But we're talking about data compression today, and those are very particular, nice codes. Here's an example of a code. So we have 4 symbols, A, B, C, and D, and here's a code word for each. And this code has the property that if I get a transmission, for example, this one here, I can recover the original string. So you could imagine having a code where that's not the case, and that would be a lousy code. But we want to build awesome codes, and awesome codes should be uniquely decodable. So we have a uniquely decodable code here. Here's another code for the same strings, and that code has different lengths for each code word. It's also uniquely decodable. But suddenly you'll see that some things are rather easy to compress, and other things not so much. And that's because we're effectively implicitly defining a probability distribution over those symbols by giving them code words of different lengths. So if we expect to see a lot of Ds, then this might be a very useful code to use. And if we expect to see a lot of A's, then that might be a lousy code to use. But either way, both of these codes, right, are uniquely decodable, and they have different properties. This code, incidentally, is optimal if our distribution over the letters is uniform, right? And that's corresponding precisely to the decision tree we had earlier. You can kind of see it. And here, we have a decision tree that decides, is it D or something else? And then the next decision is it C or something else? And then the last decision is it A or B? Those are the questions, if we made this into a question answering game, that these codes would be asking. Now, it turns out that there's some beautiful theory underlying this. And now that you all have an intuition on how codes work, I'm going to point to one of our heroes here, which is Claude Shannon. Claude Shannon essentially came up with information theory all by himself, and he published it in like one paper, and everyone was depressed. There was nothing more left to do. He essentially solved everything: error correction, data compression, one paper, done. It's amazing. Like, you know, if you can do something like this, you know you've got it made. That being said, he started a whole field where there's still tons of papers published every year, so he hasn't done everything. But he essentially like started the whole thing. So he defined communication as the problem of reproducing at one point a message selecting at another point. For us, it's going to be exact representation, right? Here's the dude. He looks kind of intense, right? Do you see that? Like, he was the dude. Oh my goodness. And that was the paper. Beautiful paper, well worth reading. And it's not here. But yeah, you should look it up. So, the way that Shannon thought about the world was communication is essentially as follows. We have two participants. We have Alice, who wants to send a message to Bob. And they're going to use a communication channel Z that might distort the message during the transmission. So Z is effectively a probability distribution, right? A conditional distribution that gives us this distribution over Y given X. So depending on what Alice puts into the channel, we have a certain chance of getting things out on the other end. And it turns out that if the channel is very noisy, we may have to do a lot of work to ensure that Bob can decode the original message that Alice intended to send, and she will have to do something to that message in order to make sure that the errors that Z, the channel, will introduce can be compensated for. So Bob, of course, is interested in decoding X from Y, and he has agreed a code with Alice in advance. And of course, Bob is a sensible, rational, reasonable person, so he uses Bayesian inference, and he applies Bayes' rule to the problem. And so, just to be clear, examples of channels include pretty much everything. So, sound waves in air, that's an example of a channel. Electrical signals in copper wires, magnetic tape, radio waves, punch cards, that's a pretty interesting channel, actually, because you can always make more holes, but you can't remove holes easily. But nonetheless, it's a communication channel. DNA is a communication channel. All these channels have different properties. They preserve different messages differently well. They introduce different kinds of errors. And DNA in particular is a fascinating example. And for each of these things, right, so we might be sending a message from one place to another place, or a message from one place to the same place, but in the future. Each of this is kind of an application of a channel. So if you write your file on a hard drive, you leave that hard drive to rot for 10 years, and then you attempt to read it again, you'd better hope that whoever designed the hard drive had some aging of the materials in mind and had a corresponding channel, a model for it, and a code that will compensate for some of the distortions that are created in it. All right, so typically we can't really alter the properties of the channel. Sometimes we can find a better frequency where there's less noise, or sometimes we can switch from magnetic tape to optical discs. But typically, we're not really able to change the channel properties themselves. But we can choose the input distribution that Alice will use, and that essentially determines what code we can choose. So that's, on a high level, how we can think about making codes that fit particular purposes in communication. Now, here's probably the central most important thing that Shannon gave us for data compression, and somehow the math is not lining up. So close your eyes for a second. I'm going to try and reload that slide. Is it coming? Yeah, well, looks a bit better. So the information content of a p-distributed object is essentially h of p of x bits. This is called the information content, and it's given by the logarithm of base 2 of 1 over the probability. Whoa. Okay, what's this? So effectively, this tells you in bits how much information is in a particular occurrence of a particular event. So remember when you gave me a yes and no answer earlier, and I said that's 1 bit of information? Now, it's 1 bit because it had a probability distribution of 50-50. It had a 1/2 chance, and taking log to the base 2 of 1/2 gives me exactly 1 bit. If we had a probability of 0.25, for example, then what we would get is 2 bits, right? But we can put any number in, and we will get the corresponding number of bits. And that's pretty fun. And the question is, what does that even mean? Like, can you give me half an answer to a question? Like, what's half a bit of information? We're going to get there. Bless you. All right. So here's a puzzle for you. I'm going to let you think about that for a minute. So what sort of probability will give us an information content of half a bit? What sort of thing needs to happen that will say, that was half a bit of information for me? That's kind of weird, right? Like, if I'm thinking about a bit and I'm thinking, hey, dudes, like, it's a yes or a no, which one is going to be, and it's 50-50, that's 1 bit of information. But what's half a bit? Like, that's pretty weird. Well, the answer is kind of here. But I'm going to let you think about that for a while. I'm not going to give you the answer because I want you to think about it. Because when you think about it, you're going to learn something interesting. And I think it's more important to learn it than to have it spoiled. And if this is easy for you, hands up, if this is too easy for you, is this easy for you? Who finds this too easy? All right? So we have also a second puzzle, which is learning the opposite. So if you flip a bent coin and you observe the outcome, so it's a 1 or a 0, because all coins are labeled with 1s and 0s these days, especially bitcoins, then you learn, say, W bits of information by observing the outcome. So if it were a fair coin, right, where it's half-half, you would learn 1 bit of information. We already know that. But if it's a bent coin, we're going to learn a different amount of bits of information, depending on what the outcome is. My question here is, how many bits would you have learned if the coin had landed the other way? Also pretty fun. I'm going to let you think about that too. And while you think about this, I'm going to try and make it harder by distracting you and talking some more. So I introduced information content. And the next thing that I'm going to introduce is information entropy. And it's really the same as information content, but weighted by the probability of the thing that we're considering summed over all those things. That was incomprehensible, wasn't it? Okay, so I'll try again. So effectively, the information entropy is a measure of a distribution. It tells you how random a distribution is. If the entropy is high, that means it's pretty random. And for discrete distributions, the highest entropy you can get is if the distribution is uniform. So a uniform distribution will give you a high entropy. Also fun, exactly how much entropy does it give you if you have a uniform distribution of n things? Useful to work out, and it's surprising. But more generally, if you have a distribution that is not uniform, that is somehow different, then that means you can probably compress messages that come from that distribution. So if you have an element that is distributed according to P and P is not uniform, you can totally build a compressor that will make the message smaller on average. Of course, as we learned earlier, it's always possible to have a message that's adversarially chosen that will get longer with that particular code, right? There's no way around it. We already know that. So entropy essentially is the expected amount of information per thing. And if it were uniform, the amount of information for each thing would be the same, right? But if it's not uniform, it will be different, and it's weighted by each probability of each outcome. So here's an example of the information entropy of a few distributions. So this one we know, right? So having a choice between 0 and 1 gives us 1 bit of information. That's because the entropy of the distribution over 1 and 0, that's a half, is 1 bit. If we have 3 things, then we get this number here. So that's the entropy of a distribution, a uniform distribution over 3 equally likely choices, and so on. And interestingly enough, if there's no choice at all, that's 0 bits of information right there for you. And you're still working on the half bit that I asked you. So that's cool. And so here's what happens if we make the distributions non-uniform. So here's a uniform distribution over 3 things. If I allocate the probability slightly differently, so here, they have to sum to 1. So 1 is represented by the full length of the box. B is the most likely symbol. B has a probability of a half, C has a probability of a quarter, and A has a probability of a quarter. That gives you an entropy of 1.5 bits. And the way to think about it is that on average, if you communicated messages, that's the amount of bits per message that you would communicate, right? But that's assuming that each person knows that probability distribution. Here, similarly, it's possible to have a distribution that has an entropy of 1 bit, even though there are 3 symbols in it. There are many different ways of constructing this, but this is pretty fun. So here, on average, right, there's this weird number here and here, like the probability mass for each of these 2 symbols. But effectively, on average, I would communicate 1 bit per symbol. And that's what it means to say the entropy of that distribution is 1 bit. And here, again, right, we can go lower than 1 bit even. So here, the outcome C, right, that symbol is so extremely common that on average, it brings down the amount of information needed to convey that. So we can, on average, communicate we will have 0.66 something bits per symbol. And again, it's maximal if it's uniform, and you can't go higher than this with 3 symbols. Just because it's so fun, it is actually possible to define a distribution that has infinite entropy. And sometimes that gets people because they feel like clearly entropy is a measure of how well I can compress. Turns out this is not necessarily so. So here is a distribution that's perfectly well defined. C is some constant. It's just the normalizing constant that you can work out. But it has the property that it has finite information content for everything. So you can definitely write a compressor that compresses this, but it has infinite information entropy. But anyway, information entropy isn't important for designing compression algorithms, even though some textbooks claim that's the case. It's not. Information content is. That's what really matters, and that's what determines what you can and can't compress and how much you can compress it to. All right, so we can extend the concept of information entropy to joint and multivariate distributions as well. So just like you can have joint probabilities, you can have joint entropies. I don't think it's interesting enough to really go into it, so I won't. You can also define conditional information entropy, and it all kind of just makes sense. And there's also an important concept related to the conditional probability, which is the mutual information. The mutual information between 2 random variables essentially lets you work out what the channel capacity is when you want to figure out what is the maximum rate at which you can communicate over a given channel. Things like that. But we're not going to talk more about channels. We really just want to figure out how we can compress better and how we can talk more about compression. So the goal of data compression is to construct some code C that minimizes the length of the transmitted message. So we still want to communicate the same movie, the same novel, the same text, but we want to spend as little bits as possible as we can. So if, for example, you imagine you're somewhere on a distant planet, you just wrote the most brilliant novel that definitely everyone on the internet must read, but you have to send this to Earth somehow, and the bartender in the bit bar charges a stiff fee for each bit. Goes like, well, you know, I'm going to charge you for each bit. And you're like, well, I'm going to have to think about this. Like, how can I send my bits in such a way that I will pay the least and maybe just write a longer novel, because everyone likes longer novels, right? So that's the idea. But the sender and receiver have to agree on that code in advance. So essentially, we need to have some basic way of communicating, and we need to have an agreement between the sender and the receiver on what the code is going to be, and that code should be designed in such a way that the expectation of the thing that you're transmitting is that the expected length is minimized. Oh, there we go. So, I know you're all very tired, but I'm going to present a magic trick to you, and we're going to do this and then take a little break, because it's good to have a break, refresh a little bit, and then get back to it with a fresh mind. So the magic trick is as follows. There's a magician who has 125 cards. Each card has an integer written on it, and in total there are the integers from 1 to 125. But the magician isn't actually in the room. The magician is somewhere locked in a box, and he can't see what's going on. And while the magician is away, a volunteer who helps the magician, a volunteer from the audience chooses 6 cards from that deck of 125 cards. That's maybe a bit easier to read. So the volunteer chooses 6 cards from the 125, shows them to the audience, so everyone knows what they are, and then he gives 5 of those 6 cards to the magician's assistant, who is also in the room and can also see everything. So the volunteer hangs on to the 6th card and doesn't tell. Now, the assistant goes and he walks up to the box, he opens the box just a little bit, and feeds the magician the first card from the 5. It's like, here's a card that was picked. And the magician's like, oh, I don't know. I can't tell you what the other ones are. And then, you know, he gives him the second one, and the third one, and the fourth one. And after the magician sees the 5th card, the magician says, oh, I know what the 6th card is. I can totally predict what that is. And before you go on to the break, what I want you to figure out is, how does this trick work? I've essentially given you the essential tools earlier in this talk. So just to be clear, there's no cheating. So it doesn't involve that the assistant is sort of having a walkie-talkie or sending a text while no one's looking, or writing it on the card. So there's really no cheating involved. So the volunteer chooses 6 cards and chooses 5 of these to give to the assistant. The assistant gives them one by one to the magician, who couldn't see any of that, and the magician can predict what the 6th card was. I want to know how that works. Does anyone have a question about that?
Yeah. Does the assistant know the cards?
Sorry?
Is the assistant aware of the 6th card?
Yes. So the question was, is the assistant aware what the 6 cards were? And yes, the assistant knows what the 6th card was. Question there? No, the volunteer can choose. So the question was, do they have to be in a particular order? The volunteer can choose any 6 cards, and he can give any 5 cards to the assistant. So the card that he keeps can be the lowest, the highest, or any from the middle. Question there?
Can the assistant choose the order in which he gives the cards to the magician?
The question was, can the assistant choose the order in which she gives the cards to the magician? And the answer is yes. And the magician can, of course, have an agreement with the assistant in advance. So when she is predicting what the card is, right? So she's hidden inside the box, and she's predicting what the card is. She can have any sort of agreement with the assistant in advance, but they can't communicate other than through the 5 cards being passed. Any more questions, or is the problem clear? No? One more question? Sorry, I couldn't hear that. Can you repeat? Oh yeah, you're asking if the card has a direction. Let's let's assume that the cards don't have a direction. They have the same number printed on both sides. All right, enjoy your break, and see you here in 15 minutes. All right.